Let's begin with a question which I'd like you to keep in mind as you go through the video. Learning or reverse engineering the XOR function requires more than one neuron. Each of those neurons, each of those multiple neurons that we are going to use can suffice with only an affine transformation. We do not need an activation function. Only an affine transformation is enough for each of the neurons in learning the XOR function. Learning linear regression using a single neuron didn't seem too difficult. Let's now turn our attention to a slightly more complicated function. This is the XOR function. XOR will take in two inputs, which are both bits, so they can take values of 0 and 1. The output of the XOR function will be 1 if each of these inputs is different from the other. If either both of them are a 0 or both of them are 1, then the output will be 0. Now, let me tell you upfront that reverse engineering the XOR function will require three neurons arranged in two layers, and it will also require us to make use of a non-linear activation function. When you hear this, very likely your question is going to be, how do we know? How do we know that this particular arrangement of three neurons arranged in these two layers is going to learn XOR? And the answer is, well, some previous researcher has found it out. This brings home one of the challenges of working with neural networks. Your job really is to experiment with different architectures and ultimately settle on some architecture which meets your purposes. It ought to be ideally the simplest architecture which can learn the function that you are interested in learning. So do keep this in mind for when you are building your own neural networks for image processing or text processing or whatever. The hard part of that job really is trying out different architectures and finding one that works and is not too complicated. Returning now to XOR. XOR is typically represented using a truth table rather than a pseudocode representation. The truth table is very succinct. You can see that it tells us at a glance how the output Y depends on the inputs x1 and x2. XOR is a very famous example of a function that cannot be learned using a linear activation function or just an affine transformation, and that's because XOR is not linearly separable. Let's understand what exactly that term means. Given that there are two inputs x1 and x2, let's represent these along a pair of axes, x1 along one axis and x2 along the other. Now, let's go ahead and plot the values of y corresponding to the different combinations of x1 and x2. For instance, when x1 and x2 are both 0, y is equal to 0. So we write y is equal to 0 for that point at the origin. From our truth table, we know that when x2 is equal to 1 and x1 is equal to 0, the output y is equal to 1. Likewise, when only x1 is equal to 1. And lastly, when both of the inputs x1 and x2 are equal to 0, the output y is going to be 0 as well. So we end up with 4 points in our two-dimensional space. Now, here's the deal. Try drawing any straight line through this plane such that it divides the points into disjoint regions. In other words, try and find any straight line, if you can, such that all points on one side of the straight line have y equal to 0 and all points on the other have y equal to 1. No matter how hard you try, you will be unable to find such a straight line. And this is why we say that XOR is not a linearly separable function. This bit about linear separation has to do with a particular type of neural network called a single layer perceptron. A perceptron is really just one neuron. It represents the simplest type of neural network. In TensorFlow, however, we tend to model neurons and neural networks using directed acyclic graphs rather than geometrically. Perceptrons are more of a geometric representation, and that's why while working with TensorFlow, we tend not to talk about them at much length. In any event, it is not possible to learn the XOR function using just one perceptron or just one neuron, and we're going to need a more complex neural network like the one that you see on screen now. Once again, don't worry about how the folks who came up with this architecture knew that it would work. That's beyond the scope of this course. Instead, let's focus on how this architecture is trained and how, once it's trained, it's able to perfectly reproduce the XOR function. Let's go ahead and double click on this network. We're going to open up the individual neurons. So the inputs x1 and x2 will both flow into each of the neurons in the first layer. Each of these neurons in turn will have both an affine transformation and an activation function. Each of these building blocks in turn will have their own weights and biases. Then the outputs of these two individual neurons will be passed into a third neuron. That neuron will also have an affine transformation and an activation function. And the output of the activation function of that third neuron will represent the output of the neural network as a whole. And that is what needs to match the truth table of the XOR function. Let's now break this down. There's a lot going on here. So let's parse this. Let's start with the first neuron. X1 and X2, both inputs will be passed into neuron 1 as the inputs into the affine transformation. There will be a couple of weights as well as a bias. The second neuron also will have the same structure. That's why these are in the same layer. Once again, both inputs will be passed into each of neuron 1 and neuron 2. Both neuron 1 and 2 are in the first layer, but neuron 3 is in the second layer, and that's because it receives as its input the outputs of the original two neurons 1 and 2. Let's now zero in on the activation functions of the layer 1 neurons. The XOR function is not linearly separable, and so we need some nonlinear modeling in there somewhere, and this is what the activation functions provide. The activation functions that we are going to use on both of these neurons will be ReLU, that is the rectified linear unit, which we already alluded to. ReLU will basically output the maximum of 0 and its input. So if you pass in some input x, the output of the ReLU activation function is simply going to be max of x comma 0. So let's go ahead and pencil in ReLU as the activation function in each of the neurons in our first layer. Notice that this is a change from the linear regression case. There, because we did not require any nonlinear elements at all, we made do without an activation function. The affine transformation was all that we needed. These ReLU activations will take the outputs of the corresponding affine transformations and chain each of them into the input of the layer 2 neuron. Now it turns out that this much non-linearity is enough for our neural network to learn XOR. The activation function of the layer 2 neuron does not need to add any further non-linearity. And so here all that we need is the identity activation function. The identity activation function just takes whatever input was passed in and sends that out as the output. The identity activation is what we had made use of implicitly when we modeled linear regression using a one neuron neural network. This is now a fairly legit, a fairly serious neural network. It has 3 neurons arranged in 2 layers. Let's be clear on what the inputs are. They are x1 and x2, which pass in equally to each of the neurons in layer 1. So in a TensorFlow computation graph, x1 and x2 will be placeholders. The output of this entire neural network is the output of the activation function of the last neuron in the last layer. Neurons 1 and 2 together constitute layer 1. That's because they are logically similar. They have the same structure. The third neuron, which is by itself in layer 2, has a different structure than the other two previous neurons, and more importantly, it takes in as the inputs the outputs of the first layer. And in this way, information only feeds forward in this particular neural network. Not all neural networks are like this, by the way. This is a specific type of neural network known as a two-layer feed-forward neural network. Now, we mentioned that the inputs x1 and x2 are placeholders in a TensorFlow sense, but that still leaves a whole bunch of variables because each of the neurons has weights and biases, which are TensorFlow variables. The values of these weights and biases will need to be determined during the training process. We are not actually going to implement this XOR neural network in TensorFlow, so we will not specify optimizers and so on. We will, however, go through the workings of this neural network in painful detail. And we shall see how the values of these variables are what allow this neural network to really learn and to reverse engineer the truth table of the XOR function. Let's turn back to the question we posed at the start of this video. Learning or reverse engineering the XOR function is going to require more than one neuron. That bit is certainly true. But as we saw, the second clause of this statement is false. That's because XOR is not a linear function. There is no way that we can create one line to separate all of the points, the different outputs of the XOR function in a plane. Because XOR is non-linear, it's not linearly separable, we need to introduce some non-linearity in our neural network for it to be able to successfully learn or reverse engineer XOR. So this statement on screen now is false. We require multiple neurons, and those multiple neurons will require activation units.